Hello, hello. Another random stream off schedule. A very short one, probably hour, maybe 2 hours, depending on how it goes. Let's work a little bit on current sensors and see where it gets us. First, let's start spinning the motor, the most important part. And to do so, let's just flash our example. Run. And we have a spinning motor. Start is good, start is good. Let's keep going. First things first, let's actually look up the code I wrote before. Like yesterday was another random stream where we were doing some cleanup, and maybe we will continue doing cleanup today as well. Just focusing more on ADC implementation, like rough ADC implementation, because there are quite a few questions in ADCs. And I'm not a huge expert, so don't rely on me too much for advice for now, but maybe later. We were discussing that we have a plan eventually to do a stream looking Texas Instruments, like watching Texas Instruments ADC course, so we might as well do it. Actually, we might as well do it relatively soon, but like first things first. Let's get stuck first before we will do anything more. Okay. So now let's read our code. This is not the one, this is not the one, maybe this one. Let's find where we had our old implementation of the FOC, because we had it somewhere. That doesn't look like it at all. That looks rather tiny. Maybe here? Oh, that looks way better. And we have quite a lot of things here. Let's read the code. Let's actually read and clean this code because it looks very useful. Let's set this configuration as active. Let's run the first build to see our errors, because I do believe we haven't cleaned it yet. So things might as well break. All right, that is not important for now. I just comment it out. I was experimenting off stream. Don't mind me. This is as well. Okay, okay. Things keep breaking. This is fine. This is easy to fix. Because I changed the file structure and we need to provide the include path. To where exactly though? Oh, I remember. It should be here. And also we need to edit here. Okay. Should build now. Yep. Another issue here. Quite a few actually. Okay, this function was renamed like this. Very easy fix. What else? This was renamed to counts. Also an easy fix. Oh, I just pasted my title. Don't mind me. Counts. Should be much, much better. Oh, it's actually solved most of the issues. Okay, this is a very nice find because it says that we are using a constant that is double, which we don't supposed to use. Easily fixable as well. This can be ignored. And we use the same constants here. Let's fix it. Easy fixes, easy fixes. Sounds like we are building fine. Let's see if we have any errors or warnings. Okay. And where is it defined though? This is not a big deal. This is a big deal. Oh, this is actually a huge deal. Holy, wait a minute. This is a huge deal actually. Let's add the file we need. How did I not catch it before? And we should change this to the floating point unit to F32 because currently it is double. And double are not very healthy for microcontrollers. Same thing. Looks nice. I'm glad that yesterday on stream we found the flag that allows compilers to show us error warnings when it detects that we are using double. Because in embedded systems we would want to never actually use double unless you have very good reason to do so. Because no controllers support it hardware-wise, only software-wise, and software floating point calculations are very slow. So don't do it. Don't be like me. Okay, this is fine. Any other warnings? I have no idea what this means. I will need to read it later, and this is absolutely unimportant. Okay, we're good to go. Let's start reading our examples. Yes, we will definitely found an FOC implementation here. Sounds good to me. First example of nothing, which is correct, because we need to have a fallback solution where we can go to if we flash something absolutely terrible. We need to reflash very fast, so this is a very nice function to have. This is something that probably is not needed anymore. So it is a test, ADCs and timer synchronization. Very interesting. I don't remember what it does. Let's figure it out. So this makes sense, makes sense, makes sense, also makes sense, also makes sense, absolutely does make sense. This makes sense. This as well. Right, this is very basic stuff we do all the time. So this makes sense, this as well. Okay, that also does make sense that we need to read ODC first time. Okay, that is a bit ambitious, let's say the least. Enable interrupts, alright, makes sense. Move to a fixed position with highest current in phase A. This is an awful thing, and I'm not sure why. Oh, maybe I know why it was not flagged as warning by compiler, probably because it is an implicit conversion to load 32, which is fine by us. So we move motor to a fixed position. Why though? With highest current in phase A, but we sent 0 as our voltage vector. Size very interesting. I'm not sure what it does for now. Then FOC voltage vector signs, voltage vector length. Okay, this is also supposed to be F32. And what do we do next? We push some voltage here. This example definitely lacks a comment to explain why is it needed, because I don't understand it now. Okay. Because we hold the voltage pretty constant. Like, no, we hold the current voltage vector in the same location, angle-wise. And we'll only change the voltage. So what do we test? We don't measure anything as well. Nothing is measured, nothing is saved. So what does this example do? Now what do we have in the interrupts? Maybe we measure something here. So we do start profiling. And our interrupt handler measures both currents. Starts next sampling fine, toggles fuzzy fine. Clears interrupt fine. It does not do anything useful. Very interesting. It is a nice example on how to set up ADC. Actually, maybe it is what it's supposed to show, like how to do it. Like maybe it doesn't supposed to measure anything, so it's maybe fine. Let's keep it as is for now. Let's see what else we have. Calibrates ADCs when no current is flowing by averaging 64 readings as float values and converting it into I3C by rounding. Looks good to me. So makes sense. If we want to calibrate, we need to have no calibration beforehand, which is correct. This makes sense, that makes sense. This as well. I probably used to need to use Clank formats instead of doing it manually, but get my autism. I just see styling issue and I just need to fix it myself. Okay, this should be like this. It's much more readable. Averaging and accumulators. Okay, so we wait for 64 measurements, start sampling, which is fine. 50 microseconds, which is also fine. This is roughly, this is not roughly, this is exactly how long our FOC period is, and therefore our ADCs are supposed to measure faster than this frequency in this period. So it is absolutely fine. Absolutely fine there. At here, when we are at 64. All right. That does make sense. Okay. Actually, let's run it then. Looks very good to me. Sec to sec, 1 second delay. Looks fine. Let's test it. This was an example too. Okay, let's set up our configuration. Experiments. Looks good to me. Debug. All right. I hate the latest update of the QID. One moment. I need to restart the debugger. Looks much better now. Let's flash it again. When it dies, it did die, so let's do it. Well, Warsaw. Actually, Warsaw, I did check the thing we were discussing yesterday about microcontrollers, about the versions with 3 and 5 ADCs. And the interesting thing that actually I cannot put any of the ones we found directly into the board for it to work as we discussed, so that we can offload the ADCs to like other ADCs, not 1 and 2, but like 3, 4, and 5. And the issue is how ADCs are routed. If you're interested, I can show you exactly the issue. Like the main conclusion is that I just simply cannot do it. I cannot like resolder new microcontroller in to get like better ADC placement. I will need to redesign the board. Like it is possible. I actually checked my PCB files. I have a changelog there with a to-do list. And inside this to-do list, there is actually a task to separate ADCs to upgrade microcontroller. I just expanded it based on the microcontrollers we found. But it seems like I was aware about it like a year ago. How are you doing? So here, let's see our calibration values. Oh, 1 ADC is enough for what exactly? What variables do we need? This array and that array. And let's see our calibration values. $11 and $12. Sounds all right. It's quite a bit. Wait, I'm confused from your answer, Warsaw. Are you saying that AI said that you need 2 ADCs for each phase? Because, like, maybe you're just not explaining it expressively enough. Like, you need 1 ADC per phase, and perfectly, in the perfect scenario, another one for everything else. For like voltage measurement, temperature measurement, like, or multiple temperature measurements if you have multiple of them. So. And the issue with your suggestion yesterday, where like if we can just pick a more beefy MCU and just place it instead of current one, it just will not work with how the PCB designed currently. When ADC for all phases? Oh, no, I hate it. I actually hate it. I think AI is wrong. I actually think it is wrong. It may be enough for a low-end motor controller, but there is like a very, very good reasons to use 1 ADC for separately for each phase. Like it can be quite a high-end discussion, but like if you're suggesting what AI said, like you probably don't have like your own opinion in a way. So like we can discuss it for sure. Like I can explain why it is important, but I'm just like saying from the perspective that I don't want to argue with the AI. Yes, switching between them is fine, but the issue, let me actually draw it. So we were actually talking about it yesterday. So we have a time and we have our period in this time interval. And this is like FOC period. So FOC is supposed to like PWM starts here and here. Period. So what happens when you control motors using PWM is that PWM looks like this. So for example, let's say our PWM like currently like roughly half. So what you have is this shape of the voltage that is outputted onto the motor phase. And the issue is like, let's say this is current. The issue is that current doesn't have this shape. The current goes like this, so it roughly rises here and it falls here. So when you measure this ADC, for example, let's say we are working with suggestion you gave me. So let's, for example, say that we measure half the phase with one channel, let's say channel 1, and half with like channel 2. They like, and the phases have different current shapes, but we will use this a single shape because like it roughly explains the reasoning. It's not quite, but roughly there. So I hope you can see the issue, that we will have very different averages here and here. And these averages introduce an error, like a quite significant error for the FOC. And this error can be fine if we are talking about like not precise applications, like not precise position control or not precise force control, like for a hobby project. But I am very how to say it properly, selfishly believe that what I'm doing is higher than a hobby project, higher end than a hobby project. So I would like to do it like more professional-ish style. And when we're talking about more professional-ish style of implementing this, is that no matter at what point of this shape we are measuring, we better measure at the same time. And even more, we better measure for as long of a period as we can. So if we can measure the whole period, we will get like a very good average value for this period for every channel. So that's why I believe personally, and I think it's very good reasoning, at least if my explanation was clear enough on why it is better to use separate ADC peripherals for different channels, and also why we need a separate separate ADC for other channels, because like if we would like to have all our period for current measurements, like we don't have time to measure anything else, so we need a separate ADC that will measure like temperature, voltage, like temperature 2, like whatever. Because our first ADC measures current on one phase and our second ADC measures current in like second phase. I hope it gets the point. And I'm sorry if I sounded a bit like offensive. I didn't mean to. I hope it is clear. Like if you have any other questions, please ask, like let's discuss. Perfect. Perfect. I'm glad it sounded reasonable enough. All right. So now that we have it, our calibration code works. Well, I'd say that AI is not very good to talk to when you have limited knowledge, because it may sound very reasonable. It may sound like complete true, and AI can have like very good explanation on why it works. But unless you have like some understanding, some experience, you cannot determine a point at which it starts misleading you. Because it may not mislead you at all, or sometimes it can mislead you very heavily, and without experience, you just don't know at what point the switch happens. So AI can be useful, but I would not recommend to use AI for people with like limited knowledge at topic. So because it can get frustrating results or unproductive conversations without leading to like actual knowledge gain. But maybe I'm just using AI wrong, I'm not sure. So let's save these values for this board. And let's retest it with these values to see that the new calibration should return us zeros. Oh, I see, I see. That makes sense. That actually makes sense. If you have zero knowledge, ask me. I will try to do my best to explain it to you. But also, like, even like without knowledge, you were suggesting very good things, very helpful things. Like yesterday, like I think 3 suggestions from you were like head scratchers for me. Like I actually like spent like 2 hours today, like working through what you suggested yesterday, like checking the microcontroller, checking the code, like checking on everything, like to make sure that yes, I understand that we cannot change microcontroller because of this, that, and that, and we need to implement our current measurement like this. So like, if you have absolutely zero knowledge, your suggestions are way ahead of the people with zero knowledge, like with ahead of what I would expect from people with zero knowledge. Because I felt a bit stupid yesterday after your questions. So let's see if our new calibration values are 0 or close to 0. They're close enough. One of them is 1, but it's expected. Actually, let's try to do a longer calibration and see what happens, what changes. I think it should be, where the hell am I? It should be a simple one-line change. Or is it? No, it is not. It's a multi-line change. Okay, let's actually define a variable then. Define averaging count. Let's define it as, let's say, 2 times the value. Actually, let's define it as 4 times the value. 4 times the value, and let's do it here, here, and here. Forcefully convert it to float, of course. The same thing here. Looks good to me. Let's check if we will have different results with more counts for our averaging. Let's run it and see the values. Yes, results are the same, so these values are good to go. And now we can use these values to actually try to implement our current controller. Should we try to actually implement current control today? I'm not sure, but I'm down to try. Let's just save it to our other practical build we are working with. One moment, it is here. Okay, let me note it for myself. Oh, I actually figured out another issue. I will note 2 things. Design a way to provide a serial number for the PCB to store calibration values in an organized way. This is for the future, and for this version, calibration values for current sensors are 11 and 12. Or actually 12 and 13. Let me double check it. Examples. 11 and 13. All right. Let's keep reading our examples to see the code for FOC implementation. It's odd. When we were discussing AI, 7 people were watching. I think people came to listen for my opinion about AI and left. Rough. People didn't like my opinion. Now I'm sad. So, okay, this example works. Let's see what the next example is. Is test encoder async access main. What does async access mean? Encoder write request and report handling. Okay. Okay, that is very straightforward. It just tests single function. Okay. Let's run as a test just to make sure. And what do we supposed to see? I would imagine we're supposed to see some encoder values. And we do see them indeed. And I would imagine if I rotate it, we see them changing. Good enough. Okay, let's go next. This was easy enough. Very easy indeed. Just let me change my defines to newer versions. Because I hate wrongly commented code, wrongly designed code. It just wakes something inside of me that I need to fix it. So first example. Test simple single IRQ FOC setup main. Okay, okay. So does this example already runs FOC? Okay, sounds good. Makes sense. Let's say 1113. But should be values that we should read from Flash, which we don't have implemented yet. Sounds good, sounds good. Oh, not like this, not like that. Sounds good, sounds good. That's a bit too much. Looks good. Otherwise, okay, makes sense. Makes sense. How many zeros? 1 second. Okay. Makes sense as well. And our interrupt does what exactly? It profiles itself. Sounds all right. Okay, we'll start the request. Also right. We start ADCs. All right. After a while, we take the values from ADCs. But why are we not waiting for ADCs to finish? That's a very interesting issue. Oh no, we expect to work with values from the previous calculation. All right, makes sense. Okay, okay. Finish raw Angular request. Okay, actually do FOC and it does nothing. Okay, this is just a setup example that does absolutely zero. So let's keep it for now then. Next example, test simple dual IRQ C setup main. Oh, this is a funny one. This is actually a very funny one. Not a funny one, but like a nice one in a way it's implemented. It's kind of complicated, the way I set up all the timings, but it's also very beautiful if you think about it. So I will explain now. Let me just get to the code and I will explain how it works. This makes sense. This as well, and this, and that, and this, and that, and this as well. This makes sense. Sure. All right. This makes sense. Like this. And our interrupt. Okay, it's timer IRQ, which is the first one we call. Yes, that is correct. Okay, okay. We profile it for whatever reason. Makes sense. All right, sure. And then we have this IRQ that also profile itself. but also doesn't do FOC. It just shows the timings. But it's actually good enough, given that it doesn't do anything useful. It is much easier to explain because code is small. So what is happening is very interesting now. So as I was explaining before, this example will actually change, and will probably change today, but a bit later. So as I was explaining our timings, we need to measure ADC for like as much part of the period as we can. But giving the timing, giving the timing setups, we cannot achieve like the full period. We can achieve like 60%, let's say. I'm not sure exact number, but let's say it's 60%. So the question now is what parts of the FOC we have. So FOC is like a multi-stage process. What we do need in FOC is like measure, let's say it measure speed, not measure position, measure speed, which will be V as physics-based. We need to measure currents. We need to do calculations for FOC itself, for FOC for like current loop, for FOC for speed loop, and like if we have position loop, we also need to do calculations for FOC for position loop. This is like a rough time blocks that we need to implement. And like which of them takes most of the time? The answer is actually like these two. So how we want this to work is we actually want to finish like these three as close to the end of the period as we want. Like we have this as a target. And the reason for this is very simple, because like the closer we are to the end of the period when we calculate, and like the more fresh, the fresher, I guess, the measurements at this point, the closer to the actual values on the motor we will have when we update control systems. Okay, I think I need a bunny person. Bond, I guess. Let's continue. So what I was talking about, yes, about why do we need to be very late in the period. So when we finish here, it means that we update our next PWM period very close to the moment it's called. So let's say our period was like this and we update it to be like this, and this update will be the more precise the later in the period we do it. So this means that we would like our all calculations, all three of them, be here. Now we also have a current measurement. Let's say here, and position measurement. And the point is that those can be done in parallel because our encoder is an external device. It is an integrated circuit we communicate to. And given that in our current design it is an SPI component, we can communicate to it mostly using direct memory access, or DMA, which is a mechanism that allows us to send data automatically. You just set it up that I would like to send this message and read this answer, and say to MCU, go do it, and I will check the results when they are ready. So this is how it works. And we can do the same to the ADC, which we just say, hello ADC, start the measurements, I will get results when they are ready. And by doing this way, we have like all this processing time, oh, wrong color, as free for whatever else. So it's free time. And to achieve this particular result, what I do specifically is that I actually use one of the PWM's channels as an interrupt trigger. It's a very nice system. So for FOC, we need 3 PWMs. And in STM32, every timer that supports PWM, like every major timer, because some are not, have 4 channels. So, and this allows us to do a very, very nice trick of synchronization to PWM. So 3 channels are like whatever they are, they do PWM like somehow in their period, like whatever. And the 4th channel is constant. And it calls an interrupt, a first interrupt. So let's say this is our period, and it calls an interrupt here. Like let's say it's a constant 50%, and it calls the first interrupt like 50% after the period started. Why so? After, like inside this interrupt, as you can see in the code, like it's a very simple interrupt. This is it. We just start our encoder request and do nothing else, like interrupt ends effectively. And why do we do this? Like it is still the free time here. It's free. F, to pay respect. So when the measurement ends, like when the encoder data is received, we have another interrupt. And this interrupt already handles speed calculation, position calculation, everything else. And the point is that we know this time for sure, like it is known. Like we can calculate it. And we control this. So by doing this control, we can actually achieve this result of putting our calculation as close to the end of the period as we can. So it's a very nice system. Because if we had no tool to move our calculations later in the period of the FOC, it would be like very bad. And also, if we had to use a separate timer to call the interrupt, we would be desynchronized with our PWM. And if you are not synchronized with your PWM, like all these shenanigans make no sense, because like why do you bother with all of it if you like not calculate everything when the next period starts? So this is how it works. We just call our first interrupt at the moment in time we decide. And how do we decide it? We just profile all this code. We profile it and we know, like, for example, it takes 3K cycles. And we know that with our frequency, we have like 7.5K. So we know that we need to call this like with some error margin, let's say at 50%. And we just do it. And we do all our measurements, calculations, and have a small buffer to the end of the period, and we're golden. So this is exactly what is happening here, which we decided that we use 50% of our period as our first interrupt call. Then we start our encoder measurement call. And then in the main interrupt, we do our position measurement, our current measurements, and everything else. And that will flow into the FOC implementation very nicely, like very beautifully. I'm actually very proud of coming up with this system a year ago. I just need to expand on it a bit to make it work better. Like it actually works nice. I just want to make, for example, testing, because there's a point in time, like this point in time. Where is my drawing? Like that point in time. It can change depending on your code. When you add like a lot of code, for example, you add some logic, for example, you don't control the motor as a simple like position or speed control. You, for example, make a balancing robot or something else, and you add like 2K additional calculations. You have to make this period smaller. And I would like to add an automatic test, as like we have examples from yesterday and from today, what we're cleaning up, that would just calculate all these timings and say if we are inside the period or not. Sorry. And it will be very nice and very useful, but it is not yet done, but we will do it a bit later. Because for now, if I'm outside of period, I can actually do worse than I would have done if I just had 0 here. Which is not nice, but I'm sure that 50% works, and that is good enough for now. So this example just demonstrates how to set it up. I actually will keep it as is, just maybe comment it out more, because it's a very, very nice example. And let's see what we have next. Our next example is do your IRQ setup FOC. The name is almost identical. It just doesn't have simple inside. Let's see why not. Okay, makes sense, makes sense. Makes sense, it's all the same. In here. Makes sense as well. And here and there. Okay, oh. Makes sense. Okay, okay, sure. Absolutely the same interrupt. I think they are identical. But okay, it doesn't matter much. For now, let's just continue going and cleaning things up before we come to an example we need, which is a practically working FOC, which I have example of. I just need to clean everything up until then. Test values, it is startup encoder. Okay, now let's clean this up. Code is the same. I should definitely use a function here. Okay, this is too much. Right. And what do we do here? Get initial encoder from I see. I think I was measuring how long it takes to get data from the encoder. Actually, let's run this example. I'm kind of curious how many cycles it takes, giving the change we just made. Let's run it. An error. Counter, of course. No errors. Let's run it. All right, let's see, where are we supposed to... Okay, we are not supposed to see it at all. That is awkward. And what does this example achieve? I'm rather curious. Let's move it here. And let's rerun it. This example currently achieves not much. At least not much we can see. So let's change it up and run it. We have test values. That should have some values. Okay, okay. It takes almost 1400 cycles, which I guess is fine. Let's actually calculate it. I'm rather curious. Where is my calculator? We have 170 megahertz, and we need to... Hello, Joppy Pope 69. How are you doing? Your name is kind of funny, I'm not gonna lie. Let's divide it by 33. Not enough. Oh, actually, 33. What's going on? I am developing an motor control for 3-phase synchronous motor, which is called permanent magnet synchronous motor, PMSM, from scratch, using bare metal C style programming on STM32 on custom PCB, which you can see here. This is a custom PCB I designed. And I struggle a lot with solving bugs and learning how to do stuff properly. And I think my chat is struggling together with me. That's about it. So we do very nitty-gritty details on how to do it better, how to do it properly, or how to do it at all sometimes. Now, seeing this number, I actually would like to put here 6 millions. How long was I been doing this particular project, or doing the, like, can you please specify your question a bit more? Because like I can give quite a few different answers depending on what exactly you would like to know. And it will be much easier if you specify what you exactly are curious about. Electronics? Oh, I'm kind of old now. I guess I've been doing electronics on and off for 8 years. I'm self-taught mostly, but electronics is not the only thing I've been doing, so I'm not particularly great at it, but not particularly terrible as well. Like I can design the board like this. I've been doing electronics, control systems development, and embedded programming mostly as my main disciplines. I also was project manager for a few years on hardware development projects. So I have, like, I'm a jack of all trades and master of none at all. I can do everything and nothing at all. And now I'm just doing this project for fun because, like, I just want to put my control systems education to practice by designing a control system like fully from start to finish. Like electronics, software, modeling and stuff, all of it. I hope it answers your question. And I hope it didn't sound too braggy. So what we were doing, we were measuring times and we were calculating how long it's supposed to take. Actually, it's supposed to be 2 times faster now, roughly. Let's test it. Damn, now that I answered your question, I'm so old. It hurts. Okay, it did not become faster at all. That's curious. Oh, because I'm a dumbass. I'm such a dumbass. Okay. Oh, okay, all right. Because I don't use 170, I use 150. Okay. That's my bad, my bad. When we divide by 32, we get... I think I didn't put enough zeros. Yes, indeed. Okay. Actually, this is fine. So let's say this is our frequency that we will have on our SPI, which means that we can calculate the timing, and we just need to know how many messages, how many bytes we send to our encoder to get our data. I believe it's 3, but let's check. Okay. Start row request. Actually, it's 5. 5 bytes. Oh my. Oh, I'm an... Thank you. I forgot. I was doing like calculations. Oh, you saw nothing, and I was just, okay, yes, I'm doing some progress, and I was just showing my motor controller thinking worse. Uh-oh. Uh-oh. So yes, we're sending 5 bytes, and 5 bytes are 40 bits, and in SPI they will be 1 by 1 without a stop. So we should take this number, we should write it down for now. Let's say here. So it's 4, 6, 8, 7, 5. I think the person asked about me and left. Unfortunate. So unfortunate. So now we know that we would like to use 40 bits. So let's say we have 40 divided by this number. And this will give us time, which is supposed to be 8 microseconds. So it says roughly 8.533 microseconds, which is with our frequency of 150 megahertz, supposed to give us some like which value of cycles? How do we calculate it? We have time, so it's 1 divided by this, multiplied by this. So I'm a bit slow in the head. One moment. So how do we calculate it? We have duration of code. Okay, let me draw it. Drawing is better. So we have cycle count divided by frequency equals 1 second divided by our period. So if we know our period and would like to know this value, we put the frequency here. So the frequency by period divided by 1. Okay, that's much easier to think through than in your head. And this gives us what exactly? We multiply by 550 millions. Okay, we're supposed to have 12.8 hundred cycles, and we have 1391, which is very reasonable. So is a measurement duration, and we get practically 1391, which is reasonable because we have an interrupt call, handling of registers. So good enough. This is a very nice value to have, and the value I'm happy with. So now that we calculated and measured it, and we know that it works fine, let's continue checking our examples and continue being a dumbass on stream. So next example, please. Okay. Oh, now we're talking. This example will do an FOC. Okay. So we have PID controller. PID controller? Why do we need D though? Why do we have so many of them? Holy. That's supposed to be 24. Oh, that's quite a lot of stuff. So what does this example do exactly? It's very curious because I think this is an example that will run FOC. Oh, that's a lot of code. And that's a lot of commented code. Oh, so much. Okay, so let's read the interrupt only because I'm sure that setup is fine. We call our encoder calculations. Looks good to me. Measurements log is all right. So we do the measurement of our time that takes to run this function. All right. We handle angle. We calculate position. Okay. All right. Fault counter is an old concept when we didn't have a uint64 variable to store the position, which is fine. What else is happening here? We calculate our actual position. All right. Makes sense, but needs to be put inside the separate function for sure. Okay. Oh, this example implements even a position loop. No way. Holy. This is a speed loop. This is definitely an unproportional example. It's just too much of a jump in complexity from previous example. For me as well. I'm sure that like nobody in the chat probably understands anything from what I'm reading right now because I have problems understanding this. But okay, we measure currents. We convert bus voltages, fine. Do transforms, this is also fine. Current controller is supposed to run here, which is correct. Okay, we need to run 2 PI controllers for our current loop, which is actually right. Okay. All right. So, and here is a lot of test code. And in the end, we do what? We output our speed as a value for our oscilloscope and rotate depending on orientation we connected our motor as. Okay. So we have a position loop implemented. Let's see what targets there is. Current targets, okay. Speed target, okay. Position target. Oh, I'm ready to tell such an embarrassing story. Let's test it. I think it should work. I think it should work roughly. It will be not the best way to implement FOC, but it will work, I hope. And then I will tell an embarrassing story if people wanted to hear one. Let's go to main. Let's put 8 here and let's run it. So what it's supposed to do, it's supposed to do 10 rotations exactly. Okay, let's run it. It calibrates itself because we don't store values for now. And then what the hell is going on? Holy cow. Stop it. Stop. Brother, stop. What is going on? No, this is not how FOC is supposed to be implemented. Trust me. I was hitting current limit quite a few times, so let me rise it up a bit. My power supply was not happy about it at all. But okay, let's set our correct calibration values. 10 turns. I'm not sure it was 10 turns. It was rather like party dance of sorts, but definitely not 10 turns. I wonder why though. I wonder why. So let's run it. It's supposed to calibrate itself again, which it does. And then... What the f... Stop, brother, stop. Something is completely wrong. It looks kind of funny to me. I'm not sure how well my camera translates the actual behavior of the motor. I hope it is 60 FPS because like it is rather funny in person. Let's try to figure out why it does what it does, because it does not supposed to do it, I would imagine. So flux controller, okay. Max output is 6. No, it should be 12. And it should be a variable, a definition, but for now it's fine. Why is it called PID controller though? Okay, all the functions take PID controller. That makes sense. It's just a structure, sure. We just use dgain as 0, which is fine by me. Max output, last error, current error, oh sure. Speed controller, okay. Max output, this is a task for a current controller, which is fine. And this is task for a speed controller, and you say that 60 radians per second is our limit. Okay, let's see. 24 volts here. Let's see if the limits were the problem or not. Or if we need to start testing other parts of the code. Oh, I didn't change the example number. My bad. let's try it again. It's calibrating itself. And what will happen next? Nothing good will happen next. Sheesh. This is awful, awful. Let's say I return these values. Maybe they are the reason. Because I don't remember. Let's test it out. It's calibrating itself. Nope, still crap. Let's actually remove position controller because it's a crappy one for sure, and let's try only using our speed controller. Maybe it will work better. I hope it will. Okay, we reset it. Let's go here and let's remove the position control calculation, which is here, speed targets. Okay, so we'll remove all of this code and we set speed targets beforehand. 3, let's say 3 is fine. To do add unit to the variable name. Because I have no idea if it's revolution per second, if it's radians per second, like what this is. But let's test it. Don't be like me, put your units of measurements to your variable names when you work with physics. Okay, so let's motor do nothing because we didn't change the example number. Let's flash our proper firmware. And let's run it. So it's calibrated itself. And now... Fuck. Okay, so the issue wasn't in the position controller. Very interesting. This is definitely not how it's supposed to be. Please stop. I guess I will need to look up my MATLAB values that I was simulating very long ago to see what values I'm supposed to put inside the PI controllers. But for now, let's see if the code works as expected. So... the embarrassing story will come after I make sure that this works. Sorry, Warsaw. I'm embarrassing myself enough without embarrassing story now. I think I'm doing quite well at embarrassing myself right now. So... Here, current speed value, mechanical angle. Okay. Current speed is calculated incorrectly, I guess, a bit, but not terribly so. Yes, this is definitely the wrong way to calculate it, I guess. Or maybe it is not. Oh, that's so much confusing code. Here's encoder row. Current encoder row, so current speed encoder value row. Okay. Yes, this calculation definitely has a bug, but it's not a critical one. And we found this bug 2 streams ago in another part of the code, but let's fix it later. Let's just see if it works as expected for now at all. Okay, so current speed is supposed to be measured like this. Okay, sounds reasonable. It's radians per second. Why do we multiply radians per second by radians? By 2 pi. That doesn't make much sense. I guess I just used the same variable name because it is not radians per second at this point at all, but it becomes radians per second at this point. This is a very confusing way to do it. It's a terrible way. So, okay, current error, bit target, current speed, radians per second, sure. Update PI, and our interval is this. Okay, makes sense. Okay. So this works as intended. If we assume that encoder calculations are correct with which they're supposed to be. Start next ADC sampling period. All right. Measure ADCs. All right. Max output. Bus voltage divided by 2. Min output divided by -2. All right. Why do I do it every iteration? Oh, because I measure voltage every iteration. Oh no. Oh no. Do I measure voltage every iteration? Oh no. Let me test it again. I see. Let's see. If this value is 0, then I'm a dumbass. Okay. Alright. No, I'm not a dumbass, actually. It is not 0. But it still doesn't help us. Okay. So let's run a safe code and let's get back to our struggle. And our struggles are never ending. So voltage is calculated correctly. Why though? This is a very awkward way to do it. Okay. ADC2 data register. What? What have I done in this example? Do I even measure voltages correctly? Currents, I mean. Setup IDCs gets pointers is correct, but it does set up. How exactly? Okay. Oh, now I see it. Oh. So I'm not that dumb then. That's a very interesting find. Nigvorsa, an update of on ADC implementation. It's actually is not that terrible. I completely forgot that STM32 actually has 2 ways the EDC can measure values. The first is called injected channels, and the second is called regular channels. And the difference is that injected channels, you can have up to 4 of them on each ADC, and they have all their own data registers. And what it means is that after the measurement is done, you can read the value from these registers. directly. So you can have 4 channels that you don't have to do anything else with, and you will have the measurement available for. And also there are regular channels which are different. They are handled differently by the ADC. And the regular channels are considered like low priority. So when we have injected channels working, the regular channels stop. And how it is implemented now, which is actually much smarter than I thought it is, that I will actually draw it. It's implemented in a way that we have many periods, and our injected channels run, for example, like this. Let me get a bit closer. So this is what we measure our current with, and let's say there is another period here. And the regular channel just runs all the times that injected channel doesn't run. So it's a very long one measurement. It's a regular channel. And it just gets interrupted by this channel like every time it's needs. So it doesn't run here, or here, or here. So just one long measurement that is interrupted many times. But we are fine with this because we don't need like super high timing or super high precision for voltage measurements. So this is how it's implemented. I was kinda smart about it a year ago, not gonna lie. So, but this is supposed to mean that our encoders work properly and our current sensors work properly. And everything's supposed to run properly. But why isn't it? Maybe these values are too much. Like the simplest way to test if the controller runs properly is to remove the I gain completely. Set it to 0. 0.0f. And let's say we put here a smaller number. Put it 5. And let's do it for both controllers. And if anyone needs explaining why I'm doing what I'm doing, I can explain. But be ready to not understand it, because control system theory is probably one of the most confusing scientific disciplines to ever exist. Like, it's so confusing, it's so hard to understand sometimes. I love it and hate it at the same time. So voltage is done in regular... Yes, exactly. Voltage is done and it can be interrupted, and the interruption of the measurement doesn't stop the measurements, it just continues after the interrupted by injected channel is finished, by interruption is finished. So it just continues until it's done. So here, what do you not like here? It is done also kind of interestingly. And now I remember why I only use 2 external ADCs, is because ADC1 handles, like, there is only one regular channel you can have without a need to use direct memory access. And so voltage is measured by one ADC regular channel, and temperature is measured by the second ADC regular channel. So each ADC uses its only regular channel to measure like an additional source of voltage. And they use injected channel, which are high priority, to measure currents. So let's set it this way. Let's set this like here. And this doesn't matter at all. This doesn't matter. And let's test it again. Just need to change the example number. And that's right. Let's some more calibrate. And let's see if it rotates as we expect. It does not. Okay, will it break my fingers if I touch it? Oh, it definitely tries to. It definitely tries to break my fingers, and this is not how FOC is supposed to work. So let's actually remove speed loop as well. Let's only leave the current loop running. And let's see if it helps. And our speed loop is here. Let's remove it. And we need a current loop task. And current loop task is here, 25, good enough. Let's try it. Let's try it out. Let's try it out. And let's run it. Let's calibrate the encoder first. So the problem is in the current loop. All right. Very, very interesting because it doesn't supposed to work like it does right now. It runs terribly, absolutely awfully. Okay, so the problem is in the current loop. Let's see our values. All right. Let's see our target. It's right. Let's see our parameters of the controller, which are both here. Flux controller, target supposed to be 0 all the time. Current error, about 0, all right. Last error, output signal, that's a bit too much. Where is the target? Oh, I think it doesn't store target. Interesting. No, but the target is constant, but it's supposed to be 0. Let me check it later. Let's see the current controller as well. Can you assign default handler as an emergency interrupt button? What do you mean? Can I stop the motor if something goes wrong? I can definitely do it. I just don't have a button, but I actually can connect. Oh, you're right. I do have 2 connectors here that are exactly for limit switches, like those 2. I can actually connect a switch here and just use it to like press something to stop the motor from doing whatever it is doing now, because what it's doing now is not how it's supposed to be working. Actually, let me know that I should do it later. It's a good idea. Note for myself. Add a limit switch as an emergency stop button. Done. We will implement it later. So for now, we get absolutely awful values in the current controller. Let's go lower. Let's see if the issue is in logic, is in measurements, in whatever. Because this example worked before. I'm sure it did at some point in the past. But it doesn't work now. Let the encoder calibrate itself, as always. And then we have nothing. Absolutely nothing. Quite curious, quite curious. Let's make it a bit bigger. And test it again. It's like right now what I expect to see is the motor to just rotate with the maximum speed that is allowed by the current sensor, by the current setting. I'm sorry. And if like the maximum speed will be achieved before max current, we will just see maximum speed. But it doesn't supposed to be jumping around at all. It's just supposed to rotate very fast. Okay, so it still jumps around. So there is an issue in the code, and it is not in the controller implementation. And if it is not in the controller implementation, it means it is in feedback implementation. So let's see how our feedback is implemented, because it is definitely implemented wrong. So let's see what is mechanical angle. And let's see what is electrical angle. Okay. And actually, as a way of solving this issue, let's stop the motor from applying any voltage. What? Curious. Any voltage to faces so that I can rotate the shaft by hands without a fear of the motor breaking my fingers off. Because this is not a weak motor. Like I don't remember exactly, but I say it's like 200 watts, so it can definitely break my fingers if I'm not accurate enough. And I would like to still have my fingers available for the future. So it should calibrate again, but it should not rotate and do anything because we don't apply any voltage. And let's see the values. And okay, and let me rotate it. What the hell is happening with mechanical angle? And why is it not giving me a chance to rotate it? It fights back. Why are you fighting back? Why are you fighting back? Okay. Let's see if I have other calls of this function somewhere here. Let's go up. And up. And up. No. We don't seem to have any. So it's supposed to be playing nice. It's supposed to be not doing anything at all. But why is it doing something? Why are you not allowing me to rotate you? Stop it. Be nice. Okay. Set PWMs. Oh, I'm a dumbass. I am... Wait, am I? I am. I guess I am. I'm sorry. Terribly sorry. To stop ourselves from spinning. Oh, one moment. I need some water because my throat is sore from talking too much. 1 minute. Okay, water acquired. Let's keep going. And we need to set all of this to 0 or any equal numbers. Let's just use 0 for simplicity. And now the motor should allow me to rotate it. Because it should not hold any position. Let's test it. It should first calibrate itself. Which it did. Okay, I think there is an issue with mechanical angle calculation, but now I can at least rotate it. Perfect. So now that this is working, let's see if our encoder values on our right are behaving as we expect them to. No, the mechanical angle is definitely terribly calculated for whatever reason. It looks awful, actually. Okay. What is going on? The electrical angle looks awful as well. What are the raw values from the encoder? Because both values seem like they are calculated like randomly, like they're just jumping around infinitely. What is going on? Do we store Actually, you know what? Let's just rewrite it. I don't want to figure out why my old code is not working. Let's just write new code that will work. Right? I agree. Everyone agrees. Because I'd say that no one talking is everyone agreeing with me. Let's just start rewriting. Damn, I keep forgetting. I'm sorry, Warsaw. I'm terribly sorry. I just keep forgetting to switch my screen. But I hope you agree that rewrite it is. Okay. How do I note for myself to not forget to change my screen back, because I forgot it twice today. Okay. Let's open this to the side, because this will be somewhat useful. Let's remove this view. Let's close everything we don't need, which is almost everything. And let's open up the proper configuration. This one, let's open its main. Looks good to me. Let's start implementing it. We need to add an etc code right here. The comment is correct, but the value needs to change name. It should be factor the name we've set up. This is changed, and here it is not changed. Now it's changed. So next, we set up our driver as expected. We set up our encoder as expected. We need to do the initial measurement to calculate bus voltage. All right, makes sense to me. So what order do we do it in? It doesn't matter much, so let's do it right after we set up encoder. And we should have inverter here. We do. And we should set the inverter value, bus voltage, to the value we measured. Let's copy the calculation approach. Like this. Looks good to me. Yep. Now that our bus voltage is set up correctly, let's measure the initial angle, which we actually already do. Okay. All right, we reset. Speed loop we reset. Current loop we reset. Device M current value. This is not needed. An absolute zero angle. It's a very interesting parameter name. What it means exactly? It just means something. Wait, why shaft alignment before we do the measurements? No, it's correct, because we calibrate it, because we don't store it the calibration yet. We haven't implemented the storage. Then we do our initial measurement. And now we need to have a... Okay, we need to have an electrical angle. So electrical angle is supposed to be a part of the motor controller, not the encoder. So how do we do it properly? Example parameters, flux angle. So we need FOC parameters. Let's add them. FOC parameters. Parameters. And it will be, what is the right name? Whatever. Motor parameters. Motor FOC. I will rename it later. So all the currents supposed to be 0. We can actually copy all of it and add to do to rename it. Sure. Sip some water. And let's keep going. So a rotor flux angle is supposed to be actively calculated. This is a bit of a confusing part because, okay, this is a terrible name, I guess. Shaft alignment, or is it? No, it's fine. It's fine. It's actually fine. Yes, we will figure it out. We will make it work. Do we need to set up anything else? No, we need to set up our interrupt, which we do. Let's give it more time because why not? And a blinky example. Sure, sounds good to me. Now we need to add another interrupt handler because we don't have all of them. Okay. Not this, not that. So let's go to this example and copy the body of the interrupt handler, because they have predefined names on STM32. And this is the name we want. Just remove all the content. And inside of this function, let's copy the whole body. Okay, let's copy this body to here, because we switch what happens where, and this body to here. Oh, and I remember, we do have to set up more. We do have to set up the encoder interrupt itself. So let's not forget it, or it will not work at all. Let's just do it properly. And the way to set it up is a single line before starting the timer interrupt. Sounds good to me. Okay. And now let's not rotate the motor at all. Let's also set all zeros to phases. And what we will do is we will start testing one step at a time to make sure that we do not introduce too much code before the next break, or we will spend days debugging it. So what this will do is, this is an incorrect way to handle this. A moment. It's thus supposed to be like this. Okay. Counter sounds good to me, and do nothing. So what we should see now when we flash it is that we only should see a LED blinking once every half a second. Nothing else should be happening. Nothing else of value. Or is it? A moment. Update speed. Okay, this is wrong. And this is wrong as well, and this is wrong then. But that's fine. Let's see if our LED will be blinking. Okay. Let's run it. It's calibrate itself, and then LED start blinking. And it does. So looks good to me. It means that nothing is broken yet, which is a good sign, So what will happen next? what will happen next is we need to start measuring encoder values, like actually measuring them. And for that, we need to do some changes. We need to use different functions because we start the measurement here and we need to finish it here. So how do we finish it here? It's very simple. Okay, and this line is not dependent on anything else, which is fine. Here, like this, but instead of what? Oh, that's correct, but that is not. We do it like this. So now we're supposed to measure both speed and position properly. Let's test it. And I will rotate the shaft by hand to see if it works correctly without activating FOC so that my fingers are intact. No fingers will be hurt in the making of this stream. So let's see if it works. Run, it should calibrate itself. And then we need to add our encoder to the live expressions and check the values. So shaft position raw. Oh, it sometimes fails to read. Very interesting. I see the issue, I see. Very curious. And now it's some awful value and I don't touch it at all. And why are you jumping? Okay, is encoder broken? Why are you jumping? Alright, so maybe this is the issue. Very interesting. Let's go back. Let's go back and make the encoder slower. Can we allow it? I think we can. Let's test it with a slower encoder. Because values are not supposed to jump at all. Like, yeah, what the hell is speed of like 11K? What? Okay, let's test the previous example again, but now let's slower down the encoder. Active experiments. So from our calculations, we saw that we have 4.8 megahertz and we need to request frequency below it. So in our setup code, let's request 4, which will give us actually 2.9-ish, because the divider should have power of 2, should be a power of 2. And let's see if it will work. So let's go back to the examples, make sure that we run 8, and let's flash the correct code, active experiments. And let's restart our debugger, because thank you STM Cube IDE for working nicely. I think it's done breaking itself. Let's try it again. Okay, we have something that our compiler complains again. And where the hell am I? I'm here. Implicit declaration function setup ADCs. All right, makes sense because I renamed it just now. Beef setup ADCs. Let's try again. Thank you everyone for watching. I'm not sure if anyone understands anything I'm doing, but like quite a lot of people jump on the stream today. I'm happy about it, and I'm sorry if it is not as entertaining as some other streams. I'm trying to do my best to make the implementation of control systems and motor control somehow watchable. So let's run it. Oh, it will not work because we removed all the code to make it work by setting here zeros. So let's return the code that's supposed to do something back. Like this, and let's try again. Okay, let's run it. Motor calibrates itself, and then nope, it didn't help at all. But I now think that the issue is with the encoder, which is a nice find. So let's get back to the example we were improving, and let's test this with the same logic to see if lower frequency helps us. So let's switch build again. And now let's make sure that our frequency is low enough. Let's say even 3. Why not? I definitely need to make it define something like E6 so that I can put 3 and consider that this is like 3 million. Like something like this, because counting zeros is annoying. Let's run it. And let's see if our encoder will tell us correct numbers. Run, open up encoder. Let it calibrate itself first. And the values are jumping still. What the hell? This is awful. Why is it happening? Was it happening before? Oh, this is annoying. So what is going on? Okay. I'm getting annoyed. Let's go to the example that tests only encoder, and let's see if a standalone encoder will have the same issue now, so that we can confirm that the issue inside the encoder PCB, and I can change the encoder PCB relatively quickly. I have quite a few spares. Okay. And to do this, we need to switch build. Bring up, because the one we were cleaning up yesterday. And let's select a motor encoder, which is just 4. And let's say that instead of waiting half a second, we will actually wait the time we're supposed to be waiting, which is roughly like this, like that. So actually 90, because we calculated that our encoder takes roughly 10 microseconds. So it will give us, this delay plus 10 microseconds will give us 20 kilohertz. So everything else looks fine. Let's flash it. I'll bring up. Okay, I did a mistake somewhere. Sure, makes sense. Another build. Now it builds. Let's flash it. Don't forget to follow if you enjoy watching me struggle. Also follow if you don't enjoy it. I will appreciate it a lot. So let's see if it runs. Let's see our variable, and it stays pretty constant. And it stays pretty constant at 10 megahertz. Ah, that's annoying. So I will spin it with my hand. And it updates in real time, very fast, with absolutely no issue. Okay, so encoder works standalone. Let's see what additions to this function break the encoder. Let's say, actually, let's return to this code. This is such an annoying bug, because I'm sure that this is a hardware bug, not a software bug. And hardware bugs are annoying as hell, because something on the PCB is like wired somehow wrongly. Actually, maybe, maybe holding the encoder wires close to the motor wires is not the best idea. Let's see. We can definitely figure it out eventually, so let's go back to the code, which is not this build. Start control. Let's run it. Let's open the main. Let's close everything here. We don't need it anymore. And switch perspective. And let's remove all the code that is not needed yet. So we will remove the EDC code. We will remove the motor controller code. And the PWM will be started, but will not be used. And here we will not output anything, which is fine. But we will not output anything at all, and we will also not calibrate the encoder. So this line will be absent. What else? Everything else is supposed to be present. And let's see if encoder will work properly without motor controller and ADCs enabled and handled. Right, nothing else is handled, correct? Anywhere here. Let's run it and test it. I think so. Ah, thank you, STM Cube IDE, for breaking again. I appreciate it a lot. Let's restart our programmer. Okay, I put it in, and let's flash it. I start control it is. So let's see if our encoder will still be having aneurysms every other measurement or not. And it is stable. Is it though? Wait, I am measuring, I am not measuring. Are interrupts enabled? They are. Okay, hello. So whilst I'm not updating, why not though? Are we don't see LED blinking, so something is not fired. So something didn't fire up. Nope. Let's go back. Let's put a test point here. Oh, we never get to this interrupt. And why do we never get to this interrupt? Oh, because we didn't set up peripherals. Oh, that's annoying. That's annoying as hell. Oof. Okay, so we do need this function, or actually part of this function. And the part is that we need to set up peripherals. But if we do set up peripherals, we actually already set up everything else. Instead of setting peripherals there, what I say, let's actually add the measurement code here. So let's do it like this. Just put it to a better delay. Remove this line, remove that line. Change this delay from seconds to microseconds, from to 90-ish. And let's say we will want to do this line. That will wait for encoder data to be available, and this line so that we update our encoder measurements as expected. Only position, not speed, because we don't have precise time measurements here to update the speed. And do we need anything else? I don't think so. Let's flash it and test it. I think the lines are incorrectly spaced. It should be like this. Let's rerun it. Let's rerun it. So let's see if our encoder will update correctly, and it doesn't. Very interesting. So it still jumps around. And now thinking about it, what I think is that we use separate functions, we use different functions. Let's, instead of this, do the functions that doesn't use direct memory access. And let's not enable this. Because actually this interrupt is random. Like we should... Oh, but it enables only interrupts, so we should have removed. Like, let's remove this line only, and let's test without this line, because this interrupt was actually fired multiple times, and it doesn't supposed to be fired. So let's test without it. I'm just breaking the code in HD. Let's see. So, and our encoder measures awfully. It just jumps up and down, up and down. It's awful. What is happening? What is this? My God, stop. Okay, so what my idea now is maybe the problem is not with SPI itself. Actually, let's check the error log. Do we have any errors? We don't. So nothing obvious is breaking. Sorry. And let's check. Actually, this function is still needs to be used, but instead of waiting for starting the measurement and finishing the measurement, which we will move to the top of the line. So let's do wrong language, don't mind me, encoder, and let's say current value, and instead of waiting for the measurement, let's just measure it. Get. Oh, I have so many lines, so many functions. Let me just check what example uses. Get triangle, sure. Sure. 6835 and let's see if it will also jump. And if it will not jump, then the issue is inside the DMA controller. And it is very interesting problem to have. But it's better be this way. I rather solve DMA issues than hardware issue, to be honest, because one is a software one and one is a hardware one. Nope, didn't help at all. This looks awful. But why? But why? Let's actually not update the position at all. Let's only measure the angle and nothing else. Let's do nothing else. Still jumps. Oof. Just oof. Okay. So sometimes it even gets 0. Any errors? No errors. Okay. Send message. That's annoying as hell. So what do we do differently compared to the example? Because example works perfectly. It works on a higher frequency even. Why? Send help. I actually added emote for this. Let me find it actually. Where are my emotes? Like 7TV emote. Can I not do it here? Oh no. I don't have it installed on the... Oh, alright. Whatever. No send help emote for me. Okay. Let's compare. So we get raw angle. Sure. Sure. Is hysteresis the issue? Let's test it. A moment. An emote. Okay, we removed hysteresis. Let's see if it helps. It doesn't. So another bug hunt. Let's remove this setup. And let's remove this line, those lines actually. And let's test it again. Like at some point it should start working. Let's see. And I think it decided to not measure anything at all. Or no, it does work. Okay, so, and it works when exactly? I removed 3 lines. Let's add this line back. Let's run it. And it still works. It does. It works nicely. Okay. So... are you saying that enabling... Okay. Okay, let's not enable interrupt, but let's enable our... let's just enable PWM on the force channel. Just again. Still works. It still works. Okay, okay. We're getting somewhere. And let's now enable the interrupt. An interrupt, let's say it will not do anything useful at all. Let's run it. It still works. What? What? The fuck? Okay. Very interesting. So, all right. Let's get back our request and wait implementation and see if it works. And let's update position. Why not? Let's test it again. Let's see. And run. It still works. What the hell? Okay. Am I a dumbass? I know that I ask this question every stream, but I'm very confused right now. I'm very, very confused. So, are you saying to me that let's reintroduce hysteresis? Let's just test one line at a time, because why not? I have time. Let's run it. Still works, right? Yep. Okay. Very interesting. Very interesting. Let's say we don't measure currents. Let's say we don't measure currents. We don't measure currents. And let's say I do enable the DMA interrupt. And let's say I will enable this line. Now we'll remove all of that and put this back. And now I will hope to see if it works. Oh. Let's see. Run. Nope, it doesn't work. So what changed? Something got broken. And what have we done? We moved this code and we moved it here. It jumps around. Wait a second. Oh no, I think I know the issue. No. I think I know the issue. Oh, do I? I need a reference manual real quick. G4 reference manual. I might be such an idiot. Oh my god, no way. Direct memory access. Registers. Sorry for the flashbang. No, thank you. Now let's see. What register do we choose? IFCR. IFCR. This one. So global interrupt, flag clear, transfer complete, half transfer complete. Transfer error flag. Okay. And what do we clear from all of those? Because I do remember having a huge issue with direct memory access exactly because of it. actually, let me open up another example. No, I don't need to. I clean SHTI, which is half transfer, and I clean SGIF, global interrupt. Okay, I'm sure I need to clean this as well, which is DMA, IFR. How was it called? CTCIF3. Let's see if it helps. See if it helps. No, it doesn't. Okay. As annoying as that might be, it doesn't work, but I have an idea what is wrong. So you int32 team counter equals 0, and it will be DMA counter equals 0. So let's say we increment it every call of this interrupt, plus equals 1, and we increment it every call of this interrupt, counter plus equals 1. Let's flash it, and we will need to add both of them here. Okay, run it. What? First of all, they do happen not equal amount of time, which is incorrect and already a mistake. But why are they so slow? What is going on? They're supposed to be like 20,000 times per second. No? I'm confused. What? Do I call it in main still? But I don't call it in main anymore. It is like every start transfer angle measurement should have a stop. And as long as it has a stop that expects this start, it should work fine. But now I'm confused why the interrupt frequency is so low. That makes no sense at all. So, okay, that's very confusing. Here, peripherals, SPI, PWM, and the frequency of the timer, precision, and the value is 20K. Sure, that is how it's supposed to be. Why are... First of all, interrupts are definitely asynchronous. They are supposed to be synchronous. And more than that, they're supposed to be much faster, like 1,000 times faster. So I have two issues at the same time. Why? My God. I will definitely have a productive stream someday, but this day is not today. Okay. Okay. So, how will we solve these issues one by one? So first, let's figure out what is wrong with our frequency. And how do we figure this out? In the perfect world, I need to find a cable and attach a logic analyzer. Give me a moment. What do I have here? Not the cable I was expecting to have. Another box? Nope. I think I will need to make a cable from scratch, which I will not do on stream, to not annoy people and to not make people wait. So what other options do we have? We do have an option of, yes, I know the option. We can use our profiling to see exactly what is happening. Also, the question is, let's remove this interrupt. Let's remove this interrupt. And let's see if our delay seems reasonable, because for now it doesn't seem like it's working at all, actually. Everything is broken. Everything is broken. Nothing is working. So do we have an LED blinking? Roughly once per second. It looks reasonable to me. It looks rather reasonable to me. So let's start profiling. It should be relatively straightforward to see if we have some blocker. Let's just figure it out. First, let's see how long this function takes to do its job, which should be very fast. I would be expecting it to be like 100 cycles at most. Okay, so let's move it here. Let's move it there. Nope. Here. Let's see how long this function takes to execute this interrupt call. Let's see if any of them are, for whatever reason, taking forever. Run, open up debug. Okay, I forgot to enable interrupts. My bad. Let's do it again. My fault, my fault. So let's see if it helps. Okay. 83. 83 cycles is very fast. It's more than fast. It's absolutely fine. Okay, so this function is not an issue then. Okay. Let's then see if this function is an issue. Let's measure all of it. Okay. Let's see how long this DMA interrupt handler takes to execute. What? The fuck? What is this number even? 24 million? What? What takes so long? What? Okay, let's remove this line. Let's see what makes this function to take 24 million cycles. A very interesting find, if you ask me. Yes, it is that function. What the hell? Okay, so this function, for whatever reason, takes 24 million cycles. Quite curious, quite curious. No way. Let's test it again. I don't believe it. Like, no way it's like 24 million cycles. 24 million cycles is like 0.15-ish seconds. Okay, let's run it. Let's see. It is 24. Why? Let's add profiling code here. So let's add our profiler into this file. Profiling.pif. Timestamp encoder 1. It is, what do you mean exactly, Warsaw? Is that SPI end of transfer? Like, I'm not sure I understood the question. Oh. I think I killed the music. I'm sorry. Vibes are off. Oh, I returned the music back. Vibes are on. Okay. Let's start figuring out which exact point of this file forces us to wait for 24 million cycles. Actually, I might as well know which part. No way. No way. No bloody way. Hold on a second. Now it will be 2.4 millions, I guess. I think I'm such an idiot. No way. Let's run it. It is 2.4 millions. Yes, SPI timeout is exactly what we measure. The question now is why. Because we don't have an error. Like, error is not logged here. Oh, it is logged. Like, what? The fuck? Oh, we have SPI DMA issues again. But it was solved already. I did solve it. Why is it happening to me? And what was the issue I solved exactly? I remember, and the issue was that SPI wasn't set up properly. But now it is set up properly because values are updating. But we still have that. You know what? Let's undo. Let's remove this code for now. Let's put it. Or should we remove this code? This is so unfortunate. Let's reset my MCU by pressing the reset button. Oh, and errors jump up very quickly. Okay, that's so annoying. Holy crap. So SPI does times out. But does this affect values we are getting? Let's test it. Let's test it out. Okay. Let's see. Let's see what we measure now. Do we measure anything at all? We don't. SPI decided to start working completely. Sheesh. Why? Tell me why. Enough zeros. I am frustrated as hell. Send help. Send help. So we measure nothing. We are endlessly stuck inside the loop of waiting for DMA to finish. But we did measure something, like something was measured. So SPI works. Just not all the time. But I do need DMA. I do need to make everything work. But do I actually? I can implement FOC without it. I can just skip it for now. Let's just validate that it will. Like, it's a DMA problem though. Let's try to validate if it is a DMA problem. So let's remove the. Oh, that will be so annoying to handle. Let's comment all of it out. Let's copy it. Let's put some space. Let's uncomment it out. We will not have this interrupt completely. No, we will not have this interrupt, and we will handle everything inside that interrupt. So we put it here. Oh, no, it's fine. It's actually correct. Let's put it here. Let's still count our. Let's fix the spacing. What is happening? It's all right. Let's still measure our time counts, just in case. Let's remove this one. Start profiling. Sure, why not? My voice is failing. This should be a different flag for sure. It's supposed to be like this. And this is supposed to be like that. Like that. Like that. Okay. No way. Okay. That's so annoying. Whatever. So annoying. Whatever. Okay. Profiling, timer, and here we need to do timer. This code was actually incorrect because I was supposed to clear other flags as well, but whatever for now. And let's, instead of this line, we just call the measure line. Device encoder. Let's just copy this line. Too much typing. Too much typing. And get raw angle. Angle request. All right. Okay. Oh, sure. Okay. So this will take a while, but it should work if we've done everything else correctly. So, okay. This is fine, and we don't spin anything. Sure. Let's see how much time it works, and let's see if it works at all. How much time it takes. I can't speak anymore. I'm so frustrated. Frustration overdose. Let's run it. So counter seems fine, and the values seems fine as well. So the problem is DMA. Fuck. I'm angry. Rage. what do I put my frustration into? Okay. Okay, so encoder works for now. It doesn't work through DMA, but whatever, as long as it works, I will figure out how to solve the DMA issue off stream. I hope so, because on stream my brain is not functioning correctly. It's also kind of late here. Let's get the ADC back and see if ADC breaks anything. I hope it doesn't. Let's add this back, and let's add the alignment back as well. And instead of this grep function, let's add a proper function for now. Okay. Like that. And here we should use raw angle, which is correct. Fine. Do not enable this thing. Enable interrupts. Interrupt is handled. Let's test it. Da-da-da-da-da-da. So we do calibration, sure. And we have values that look good enough. They are relatively stable. There is a drift of sorts, but a single bit in a 21-bit encoder is not a huge issue. I'm absolutely fine with that. Okay, so it works. It does work indeed. Hooray! Okay, let's remove this and that. And let's try to use the next hour to actually implement FOC of sorts. So also we should measure how much time it takes this function to take. It takes 1800 cycles, which is more than fine. We have 7500 available, so we are roughly at 20%, 25-ish percent, but it's like 23-ish percent rather. But that's fine. So what's next? Now that we measure position, we measure speed, we measure angle properly. Okay. This line will stay here as a flag of shame. The code for the current loop should be here. Correct. So now we need to add PID controller. Let's do it. Okay. So it will be here. PID controller, F32 controller, which is correct. Current loop controller, current loop PID, let's say, equals. And let's copy values from our example. It will be just much faster this way. Okay. Starting from this time, everything I'm doing is around magic kind of complexity. So it's, if things before this were not confusing, things after this will be confusing, trust me. Okay, so what is the correct file here? Active experiment examples here. Example 8, post all our PIDs. And let's only do current controller. Let's actually just rename them. Current controller PID and flux controller PID. Sure. Let's add 5 here and 5 there. Okay, I will be 0 for now. We will increase it after we test that the controller is functional. And we also need a target for this controller, and the target will be float current controller target. And let's say amps. let's say amps, and let's say it will be 0.2, 200 milliamps, which is 200 milliamps. So now, we need to remove this. This is not needed anymore. This is not needed. This is not needed for now. We need to get our inverter back. And we need to calculate voltage vector signs. And instead of current sensorless angle, we need to get our electrical angle. But we don't measure electrical angle, so let's add a variable for now for electrical angle measurements. And to measure this, we also need to know the number of pole pairs we have. So let's add const uint32 motor pole pairs count, which is equals to 4 from my motor. And also let's add float electrical angle. It will be radians 0.05, and we need to add a logic to calculate our electrical angle. So to set the angle to 0, what we're supposed to do is we're supposed to apply constant voltage to a phase at P divided by 2 radians, so that we can measure our target electrical angle. So let's do it. To do it, we need to form an open loop vector using this function inside of setup code, and it will be test inverter. Let's say 6 volts is fine, and we need to do it m by 2. No, it will be pi 2, which is pi divided by 2, not 2 pi, as many can think. I am one of them. And let's do a dummy delay. Let's add our motor time to settle in the position. So let's do milliseconds to seconds, and let's say 500 milliseconds. After that, we need to do an encoder measurement. So device m. Actually, you know what? We need to do it before this measurement, like this. So we do all these measurements and then we put our motor, but we also need to apply our formed voltage vector to our PWMs, which is done by function I don't remember the name of, and it's okay, DRV 830. Okay, set PWMs. I'll just better copy it. It'll be much easier. Let's do it like this. Make sure there is a proper ending of this line. Let's wait for the moment, and let's do reset after we've done our calculations. So let's say zeros everywhere. Which is actually not correct. Let's do instead. It is not exactly correct. Oh my god. Holy crap, I have a lot of definitions. The correct way to do it will be to use half points. Because our FOC works from half points, so that it can go in both rotational directions. And I need an example to copy from, or actually do I? I'm not sure that I do. I rather need to DRV 820 PWM. Yeah, I need to check definitions file. Okay, and it will be frequency. Good. Nope. not this one, actually. I need a separate one, but from the same file. I need precision. And where the hell am I? Here. Precision divided by 2 in all 3 cases. This will stop the motor at a point where it will be easy for us to do FOC later. So now, and here, after we are set up, we need to set up, at this point, our electrical angle. Electrical angle will be 0.0. Because we moved our motor to angle, we're supposed to be 0 for FOC. All right. So what's next? Next is we need to update this angle as well. And we need to do it during the current loop update period. So I need to measure. Okay, what do I need to measure? I don't need to measure anything, I just need to calculate it. And what I need to understand is that my single encoder revolution is actually 4 electrical revolutions because I have 4 pole pairs. So my flux does full revolution 4 times. And therefore, I need to do probably the same function like this, but I need to compare it to this count divided by 4. Let's actually do it inside the interrupt itself. I will move it to a separate function later. So, but to do so, we need to also store a row value. So let's add a row value. Electrical angle row equals to 0. So, we will also need electrical angle previous. Where am I? Insert 2 electrical angle last previous row as well. Okay, I should push it. I can finish a current loop this stream. I believe in myself, even though I'm dying inside. I can do it. So now. How do we measure it? If our current position... I actually currently thinking about a hack to do it, not a direct way to do it. Because hacking it right now will be faster to get the results that I can demonstrate. So, and the way to hack it is, if we assume that is 0, then I can actually get my current electrical angle. I think I can use my actual position, and I can say that our current electrical angle rho is this value. Reminder of division by our encoder resolution. 68, 35 counts per revolution divided by 4. Divided by the number all pair count by 4, whatever. Let's be 4 for now. Let's do it like this. Am I correct or am I wrong? We will assume that the position is 0 at the point where we put the motor during the calibration, so it should work. It is a hack. It doesn't supposed to work like this, so it is a hack. Change into a separate calculation path for electrical angle later. All right, but it's supposed to work. I hope it does. And now to get electrical angle invariance, which we have to have, to apply proper current vector, let's say electrical angle radiance equals to our electrical angle rho, electrical angle rho, multiplied by our constant, which is rho to variance, but divided by 4. Divided by 4. Okay, let me check it. Let me make sure it is correct. I need to divide this number by 4. That means that I need to multiply by 4. And I need to multiply by 4 float, so like this. If it's wrong, we will see it very soon. Let's actually just test it without implementing the FOC, so that makes sure that we are not idiots, so that I am not idiots. I'm not talking for anyone in the chat. Let's see. I am frustrated. Let's add our variable to our live expressions. Angle radiance. Hold on a second. Okay, whatever for now. Electrical angle rho. Okay, let me spin the shaft and see if it works. Okay, shaft doesn't want to spin because I'm a dumbass. Right. Maybe I need to set to 0 to spin by hand. But I don't think so, actually. No. I need to do it here. And I need to remove this for now. Let's test it again. Ow. Let's see. Okay, it's calibrated itself. And now it's... Okay, this is good. This is very good. Very good, very nice. Very good, very nice. What the fuck? Right, my hack almost works. Like, my hack works in one direction. Okay, let's see. So it is correct. Still correct. Yes, very nice. But it only works in one direction. It doesn't work in a negative direction. Let's fix it. But to fix it, like, it's definitely a type conversion issue. That's for sure. So, and type conversion issue is curious problem to have. Curious problem indeed. So, Let me think for a moment. Yes, one turn, one mechanical turn of the motor is 4 electrical turns, yes, because 4 pole pairs. Like this big motor I have here that is waiting for its moment has 5 pole pairs, so it will be 5 electrical revolutions for proper mechanical revolution. Okay. So how do we solve the negative issue? Let's go to a better perspective. So we do this. This is an integer value, right? It is a U integer value. Okay, I'm a dumbass. It's supposed to be negative. Let's test it. I hate myself for always using qint instead of int, like as my first instinct. It causes so many small issues all the time. So let it calibrate itself. Okay, looks good. A negative rotation. Yep, works great. Maybe FOC will work today. Okay. So it works. It works. My hack works, but it's hacky. Don't do it like I've done it right now. So now that we have our angle and we have our task, let's calculate our PI controller. So, and how do I call my PI controller? I don't remember the names of my own functions. And help. Controller, very reasonable. Controller F32 update PI. And controller will be current controller. Current controller, and delta time will be 1 divided 1.0f divided by 20k 0f 0f. Okay. So, and here, should I put anything else inside a controller? D gain, accumulator gain, P gain, max output, min output. No. Last signal, current error, output signal, last error. Current error, last error, current error. So am I supposed to calculate current error outside of the PID controller? Oh, I do supposed to do it, okay. Sure. If I implemented this like this, I probably had a good reason to do so, so I will not think about it too much for now. Let's just calculate our error before calling our controller. Where am I? Getting lost. So to calculate our error, we need to float current error. Okay. And current error will be, oh, I need to also do those two. Now that we are at it, we need to actually, don't forget to start measuring currents. So we need to start our ADC start sampling. And we also need to get the actual currents. Sure. And we have motor parameters, motor FOC parameters, current A and current B. Okay, seems reasonable to me. And ADC1 and ADC2 are set up correctly, which is true. Okay, fine, great, perfect. Okay, we've done it. Actually, I will not do it for now. I will assume that voltage is constant, which is not, but it's good enough approximation for now. And here, do we need to do anything else? We do. But we might as well set it at the startup, which is updated. Fine, okay. All right, it works well. I don't need to update it manually, so the only thing I need to run my conversions. Okay. And I need to do my FOC parameters in here. And these conversions will give me the value I need, which is current target. Oh, sorry. Current controller target in amps minus motor FOC parameters current D. It is correct, but I need to update two controllers. So this is supposed to be done twice, for current controller and for flux controller. And flux controller task is always 0 in our case. Okay. Where are we? Float, flux controller, target. Amps equals 0. We always want flux to be 0. 0 amps. Not always, but always in our case, in our particular case. So we calculate this as current G and this as current Q. Nope, differently. This is current Q and this is current G and this is a flux controller. Flux, current, flux, error. Right? Okay. Seems good to me. All right. And after we outputted our value, I don't remember what this is, but sure. Actually, oh, our controller changes the angle. Yeah. This is correct. This is very true. So let's do it. Let's do it. Let's do the same calculation. Okay. I'm lost again. Here. Just instead of 810 we will do ARM ton to F32. Okay. It takes 3 values. Okay, again. ARM ton to F32. It takes Y, X, and result as a pointer. All right. Sounds good to me. Why not? Address of this variable. But just in case, let's compare it to the mass F, H, ton, to make sure that X and Y are not switched. Float, F, float. Okay, great explanation. Float. What is first, X or Y? Damn. I need to Google. Math H. Atan 2 params. Variables, 2 variables. Y comes first, right? Yes, Y is first, so they have the same. So I don't need to change the order of variables. which is perfect. Just need to rename controllers properly. Current controller PID and flux controller PID. Round up angle. This sounds fine to me. And at that point, current controller, okay. Depending on the rotation direction, we need to calculate our voltage vector differently, which is fine. Well, let's remove this and that and put a proper inverter. Nope, proper inverter. Here and here. Current controller PID. Current controller PID. Example params. Holy cow, what is it? Motor params. Okay. Okay. Sounds good. And here, PID. All right, so I think it will only work if I pray enough. Okay. Oh, am I a dumbass? I am a dumbass. Oh my. Oh my. I am a dumbass again. Current controller. Controller PID. Current error. Same for flux controller. Flux controller PID. Current error. That's much better. Okay, and after we've done all of this, we need to just point our inverter in the right place. And remove this. And just uncomment this. Okay, so we added a huge amount of code, and I'm not sure if it will build and if it will run, but if it will run, the motor should start spinning, just spinning fast, actually. So pray for me. Okay. Let's see. Okay, let's wait for motor to calibrate itself, and after that, it didn't work. Why? Oh my god. Oh my god. Can I rotate the shaft? I can, and it kinda fights me. So something is happening, that's for sure. Let's just see what exactly is happening. So let's check lines we've added through our debugger one by one. So let's see our motor FOC parameters. Do we measure currents? We do, but they are rather small. Okay. Oh, actually, let's add some eye gain and see. Actually. Let's wait for motor to calibrate. Okay, we're stuck. No, I'm not crying. You're crying. I'm not crying. I'm not. What is flux angle? Oh, wait a second. Hello. I know the issue. I know the issue. I know the issue. I know. I know. Total flux is actually electrical angle. Electrical. Should work fine. I hope. Okay, let's calibrate it. Fuck. Oh shit. I guess I have a switch. Okay, I think something in angles is incorrect. Sure. So our current angles are... Maybe our task is too small. It is not so small. Oh, angles are so confusing. Let's say 3, just in case. Let's say 4. I don't mind 4. 100 milliamps. What else? What else? I definitely need to go and make some tea. Now a question is, do I supposed to... What do you mean by steps? Do you mean resolution? It's 21 bits, so it's like 2 million something something. Let's see my example code to check if I actually set up initial electrical angle correctly, because I'm not sure I did. I'm actually not sure I did. I will definitely need to reread this theory about FOC, because I'm getting confused with angles, like what is supposed to be where. Okay. Actually, just for my curiosity, let's add m by half. Maybe we need to minus, but I'm not sure. Let's see if it helps. Not sure if it will help, but let's test it. What do you mean turn it by... You mean how many steps do I have when I... Currently, when the motor holds it, I have 8 steps. And I have 8 steps because I have 4 pole pairs. I'm sure there are 8. Like, I don't think I do even need to count it. So, encoder calibrates. What the fuck? Sorry. I'm terribly sorry. Okay, that was interesting. Maybe I need to do a minus. Who knows? But just in case it will break again, I might as well turn off my microphone so that only I am scared. I will do it right now. Okay, it is terrible. All right. What do you mean AI guessing mode? I was telling me to ask AI. No, I will not give up yet. I'm not that weak. Mama didn't born no loser. Okay. Let's look up my previous example. I'm sure that the issue is in the angle, so the issue is in the way I actually implement FOC. I just need to find its specific place. So let's go to a better perspective, open this code and see example 8 and see how I do the initial measurement. Electrical angle rho is 0 because I align motor. Okay, sure, why not? But how do I calculate electrical angle here? Rotor flux angle, rho to radians. Electrical angle rho is constant revolution. What the hell? Sure. To what point do I divide by 4 though? Motor pole plane. Oh, I see. Now you do. The plus then say maybe that's what I want to do to me when I said this is wrong. Oh. I will ask AI tomorrow if I will not handle it today myself. Okay. Why do I multiply? Hold on a second. Oh, I know why I multiply. That's all right. That's an awkward way to do it, but whatever. Sure. That's completely fine. And I start with this angle being... Oh. Being set up like what? Low electrical angle rho. Me in AI mode. I'm still confused. What do you mean by that? Okay. So there are only 2 places. And I actually don't do anything to this at all. I set it to 0 and run it as 0. And run it as 0. Run up angle. Actually, let's see what run up angle is equals to. Run up angle should be around 90 degrees if I understand it correctly. Let's see. Let's run it and test it. I see. Well, if it is a definition of AI mode, then yes, I am in AI mode. And I've been in AI mode almost every stream. I guess I wasn't in AI mode only last stream. But we didn't do anything like that advanced last stream. That's what AI mode do to you? You mean that you started guessing too much, or? Because like I'm guessing based on evidence, I think like this is the way debugging works. like you first like reduce the scale of the issue you think where the issue is, and after you reduced the scale, you just find the place and find the solution. I'm not guessing. I know exactly that the issue is in the angles. I just know exactly where. So now that we are set up, let's see what our run-up angle is. Looks good to me. It is around it is around pi divided by 2, so it is supposed to be correct. And our flux angle is something, and we are stuck. Okay. Okay. So our current actually, let's see what run-up angle will be when I will push it to the side. Okay, very interesting. Now it's 0.4 amps, it's too heavy. Okay, very curious, very curious. Can I somehow do it between? Nope. No, I can't. I see nothing useful from doing it. So our current implementation tries to force our rotor to a pole, to each pole. But it's supposed to do the opposite. It's supposed to move our rotor from the pole. And if this is the case, let's try to change sign here. Yes, exactly. I have 8 steps exactly because of this reason. You are correct. Let's see. Nope. Change nothing. Scheiße. And if I do it like this, like it was before. Wait a second. I didn't change in the right place. I'm a dumbass. I'm a complete dumbass. Okay, of course it didn't change anything because it was the wrong place to change. Okay, let's try again. This line is incredibly long for this text size. So let's motor calibrate. Okay, and oh shit. We are overcurrenting heavily. It's 2 amps. Hello. Please don't do it. I changed my mind. I take it back. Where is the line? Where is the line? Let me turn off the power supply. Okay. I take it back. I take it back. I was wrong. So something is wrong with the angle. What other options do we have? Because everything seems to work fine. We just we are pushed into the face, not out of the face, and we are supposed to be pushed out of the face. So what do we need to change? Let's start drawing. Yes, for sure. I had quite a few issues where motor was going crazy. The next stream tomorrow will probably be about implementing the stop button. So this is our motor, this is our face, let's say, and our current code wants our shaft to go here. Force, heavy force, and we need it to do like this, heavy force. So we need our angle to be 90 degrees offset. But it's supposed to be 90 degrees electrically. But we are using electrical degrees, so it's fine. So actually removing pi should have worked, no? Oof. Oof, 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 oof. Which one of these sides is cold though? Let me figure it out. I wonder which one I am working with right now. Breakpoint failed. What? Run. Guys, lots of people are watching me and watching me struggle. If you enjoy the view, please follow. I would appreciate it a lot. So I didn't catch what I wanted to catch. Again, a step over. Over. So we are catching this line. Okay. Okay, this line in this. And what if I say I do positive, not negative output signal? Current controller. Here is positive sign. Let's see, let's see. Let the motor calibrate itself, as always. Oh shit, we are at emergency again. It was again 2 amps. Actually, let me lower the limit to like 1 amp. Okay, okay. That didn't work. And I'm getting frustrated. Again. Flux, angle, flux, angle, flux, angle. I will test it again. I'm not sure why, but I think it was supposed to work. Okay. Let's see. And if it doesn't work, I will just end for today. I don't have any ideas to like keep going. I just need to watch this theory again and just to check all my math and to check all the angles. And I don't feel like doing it on stream. But I hope the next stream we will have an emergency button and also a running FOC. It would be very nice. Let's run it. Okay, this is the wrong example. Why are we here? Just to suffer, of course. This one. You can do this. No? Not today. Not today, because fuck me. Did I even get to that line or this line or whatever line? Like, what? Now I'm not sure if I get to the right line even. I'm annoyed. Yeah, this is true. If it worked the first time, no one would have seen how I tried to struggle to debug it. Okay. Shit. I have one last idea. One last idea. And the idea is to come here and to not do this. Okay. Oh, of course. You don't want to flash it because I turned off the power supply. Of course, of course. Okay. And we are vibrating again. Stop it. Oof. Oof, 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 oof. What other angle issues are even possible? Mm. Mm. What do you want from me? Delete. Are current calculations alright? They seem like they are. Electrical angle seems like it calculates correctly as well. Maybe electrical angle should be multiplied by -1. I'm assuming. I have no idea at this point. It should be a float, but whatever. I'm too frustrated to care at this point. Too frustrated to care. Okay, of course you don't want to debug because I have to remove you from power. Nope, it was a terrible idea. It doesn't work again. So what can be the issue? What can be the issue? What's the issue? What? But it doesn't supposed to work like this. What the hell? It's supposed to be fine. Wait, I broke something else? Let's at least fix it to be stably in the pole. What did I change? I removed this. I didn't change anything here or here. Or here. This should be fine. And also, what is this error? Not error, but warning. But I removed this. Stop it. Yes, all angles are in radians. It's just so confusing to get the angle calculations right. It's like you need to do p minus angle at some point, and at some point you need to like do plus p halved, and like it's all over the place, and like whatever. So I remember, like, this is actually a part of the story. I think I will not write any more code today. I will just tell a story and finish. And let's just make sure it works. Okay. It doesn't work. Like, it doesn't work at all at this moment. Okay, whatever. Hell with it. Who cares? At this point, let's just make it rotate in the open loop and deal with this. Next stream or off stream, and me explaining how I fix it. I think I will work on it in the morning tomorrow, with my brains being active and functional. Okay, let's make the motor spin. Bring up 6. Let's stop it and flash bring up. Let's make the motor spin in the open loop, so without a feedback. Hello. Okay. All right. Please flash. Okay. So, the story. The story is from a year ago and actually explains why I... what is this emoji? 10 spins, we're done. The story is about why I actually stopped working on this project a year ago, and I returned only like after a year. It's a long story to come to this moment, but I can explain why I stopped working on it. And the reason was that I spent quite like a lot of time, I'd say, like designing a PCB, writing all the testing software on the bring up software, firmware, all the tests and stuff. Took me like months and a half of like 8 hours of work days, because I didn't have work back then. Like, I work as a freelance engineer and I didn't have a client back then. So I had time to spare, and I was just actively working on this project, and I was hoping that, yeah, I will get to the position control loop and everything will become easy from there. So I was pushing myself very hard. And like, one of the bigger issues I had was like this exact angle issue, to figure out that I at some point need to do an angle like pi halved minus angle to get it to spin. And it took me like 3 days of debugging like this, and I was like very frustrating. I was like very angry, insanely so. And then I thought, I solved this issue, great. I need to push just a little bit more to finish the position loop and be happy and to go on with my life and to have like a great project that I can show as like a very high ceiling like systems engineer who can design electronics and firmware. And when I get to the position loop, I got into the issue that position controller worked terribly. It worked awfully. The error was quite huge and it was like jiggly and stuff. And I spent like 3 days on this and I got into like hella depression. Like I was puking on like even watching like this PCB and this motor because like I spent months and a half just heavily spending all my free time I had just like doing the PCB, doing the test, measuring, testing, and then I hoped, yes, like P controller is like the line after which I will be happy, and it worked terribly, and I like thought to myself, hell no, and I got like heavily depressed after this, and I'm like, I kid you not, I couldn't look at the project for like months and months over, because like in my brain just something broke, and I thought like I'm just a terrible engineer. I just am not capable of doing anything. I'm just not smart enough. So I actually put this project to a side for like a year. Not because I could have returned to it earlier. I just was busy, I guess. But yeah, this project a year ago got me into like actual depression. So that's a story for today. Good night, kids. And I see you tomorrow, I hope. Don't forget to follow if you're not following yet, if you enjoyed the stream. And if you want to see more, more of my struggles. I will do my best to solve this issue by tomorrow, so come by to see if it's working. Or not, who knows. And thanks for watching.